My name is Kyle Hecker, and this is IQE number 5 for Fluids 307. This first conceptual question states, what is a Moody chart and when can it be applied to non-circular pipes? I found this question particularly interesting because Moody charts are usually only applied to circular pipes, so I wanted to see what conditions it took to apply to non-circular pipes. So the answer to this is, a Moody chart relates the Darcy-Weisbach or fanning friction factor to a Reynolds number and a surface roughness in a graph, and then for friction in a circular pipe, as we stated. But it can be applied to a non-circular pipe if the diameter is replaced by the hydraulic diameter. And so this answer helped clear up a little bit of those questions I had about what was going on with that. So this calculation question. A fluid flowing through a pipe of 1 centimeter diameter that's 12 meters long and open to the atmosphere of 5 atm. If the velocity of the fluid is 21 meters per second and the density of the fluid is 1100 kilograms per meter cubed with a viscosity of 0.31 kilogram meters per second, what is the absolute pressure just before this fluid exits the pipe? And this can be a little bit related to like blood flow, except blood is obviously not open to the atmosphere, but it's really small diameters with your arteries. So this is a little bit of interest that stemmed this question. So first we start with our knowns, which is a diameter of 0.01 meters, a distance of 12 meters, a velocity of 21 meters per second, and an atmosphere of pressure of 5 atm. What we're looking for is the absolute pressure just before the exit of this fluid. So we're going to assume an incompressible flow and a steady state, and then the properties we have are the density and the viscosity. So to solve it, we need to get a volumetric flow rate. So we have the VAV equation, and A is pi d squared over 4, which is this here, and that gives us this value. Then we can plug our velocity times that area, and that gives us a volumetric flow rate. Now we have a volumetric flow rate equation, and we can solve for pressure. So this is a gauge pressure, so what we're able to do is manipulate this equation and solve for that P, and then we have everything, and we have all these values down here, so we can plug them straight into this equation, and that gives us a value of 24,998 kPa down here. So then we have to convert atmospheres to kPa, which is 5 times 101.325, which gives us this value here, and then we add them, 24,998 plus 506.625 kPa gives us a final pressure of 25,505.02 kPa.